Today, we're going to be geological detectives. We're learning how to read a story that was written by shifting oceans over millions and millions of years. A story that's been locked away deep inside layers of rock. For the longest time, when geologists looked at the rock record, it just seemed like, well, chaos. Just a jumbled mess of sand and mud and stone, all stacked up in what looked like a completely random order. It's kind of like trying to read a diary that's been ripped to shreds, with pages missing and everything shuffled around.
So the big question is, how do you make sense of a history book with no page numbers? How in the world did geologists find the key to unlock this planetary diary and finally start reading the story of Earth in the right order?
To solve this massive mystery, they needed something like a geological Rosetta Stone, a totally new way of thinking that could translate these chaotic rock layers into a history that actually made sense. And that breakthrough idea? It's called sequence stratigraphy. And here's the big aha moment. The fundamental breakthrough was realizing that the rock record isn't random at all. Nope. It's organized by a single, incredibly powerful, repeating rhythm. The rhythmic rise and fall of global sea level, over and over again, for millions of years. This brings us to a really important concept, eustatic sea level. The easiest way to think of it is as the planet's own heartbeat. It's driven by these massive climate cycles and the slow dance of tectonic plates. And this global pulse, this rise and fall, it leaves a predictable pattern in rock layers all across the world. It's the key. Now, while that global sea level provides the main beat, there are a couple of other factors at play. Think of it like a symphony, right? Eustatic sea level is the conductor, setting the tempo. But you also have regional basin subsidence, that's the slow sinking of the land, and then you have the local sediment supply from rivers, which decides how fast all that empty space gets filled in. To make this a little more real for you, a high stand is basically what we're living in today. The ocean is high, and we have beautiful beaches like the one on the left. But during the last ice age, that was a low stand. So much water was locked up in glaciers that the sea level was about 120 meters lower. I mean, that's a huge drop. The shoreline was miles further out, and old seabeds were just exposed to the open air, kind of like that image on the right. Okay, so geologists know about this global pulse, but how do they actually use it to decode the rock layers? Well, they hunt for very specific clues, these surfaces that act like chapter breaks in Earth's long story. The absolute first thing geologists go looking for is called the sequence boundary. This is their holy grail, seriously. It forms when sea level falls dramatically and the old seabed is exposed. Rivers start carving deep channels into this new land, creating this massive scar of erosion. That scar, which we call an unconformity, represents a huge gap in time. It's like a torn-out page in our diary, and it is the key to separating completely different packages of rock. So once they've found a package of rocks between those boundaries, geologists use this fundamental rule called Walther's Law. Now, it sounds a little complicated, I know, but the idea is actually beautifully simple. It just means that environments that are neighbors today, say a sandy beach right next to a muddy, shallow sea, will eventually end up stacked right on top of each other in the rock record as that shoreline moves. So a vertical story actually reveals a horizontal journey through time. Let's see this in action with a river delta. So, right now, you might have a marshy delta plain, a sandy delta front, and then deep muds, all existing right next to each other. But as that river keeps dumping sediment, the delta builds out into the ocean, and those environments march forward, burying the older layers. And the result? Bam! Those side-by-side environments are now preserved as a vertical stack of rock, telling us the whole story of that delta's growth. So how did geologists actually find all these clues buried deep in the rock? Well, their detective work requires a pretty fascinating toolkit, one that combines classic hands-on techniques with some incredibly advanced technology. It all starts right here, out in the field. Geologists have to get their hands dirty, looking at rock outcrops, identifying the different types of rock or facies, and trying to piece together exactly what the environment looked like millions of years ago, right on that very spot. And you know what? Sometimes the best clues aren't even the rocks themselves, but what's in them. This is where we get into the amazing science of ichnology, the study of trace fossils. And we're not talking about bones here. We're talking about fossilized behavior, the burrows, the footprints, and the feeding trails of ancient creatures. Take a look at this. This beautiful swirl is a trace fossil called Zophicos. Now, this wasn't a creature itself, it was the complex burrow system made by a creature. Just finding this one thing tells a geologist they're looking at what was once a deep, quiet, and probably low-oxygen seafloor. That is an incredibly detailed clue. But the real game changer, the absolute revolution, has been technology. This right here is seismic imaging. By sending these powerful sound waves deep into the earth and then listening for the echoes that bounce back, geologists can create these stunning three-dimensional pictures of rock layers buried miles beneath our feet. As this quote says, seismic data is basically like giving geologists X-ray vision for the planet. They can see the full architecture, the shape, the scale, those all-important sequence boundaries stretching over hundreds of square miles, all without ever digging a single hole. It's unbelievable.
So, okay, reading ancient shorelines is pretty fascinating. But why does any of this matter in the real world today? Well, it matters because this exact same technique helps us find the critical resources that, frankly, power our modern civilization.
This knowledge has huge economic significance. I'm not kidding. Sequence stratigraphy is an absolutely essential tool for predicting where to find oil and gas, valuable mineral deposits like gold, and even major coal seams. So, to find oil and gas, you're essentially looking for something called a hydrocarbon trap. The recipe is actually pretty simple. You need a porous rock, like sandstone, to act as a reservoir that can hold the oil. And then you need a non-porous rock, like shale, right on top, to act as a seal, trapping the oil and gas so it can't escape. And this is where it all clicks into place. That global pulse of the oceans we talked about? It is the perfect machine for creating these traps. When sea level falls, rivers dump all that porous sand way offshore, creating a perfect reservoir rock. Then, when sea level rises, the coast floods, and a thick layer of impermeable mud gets laid down right on top, creating the perfect seal. You just repeat that cycle for millions of years, and you build the perfect alternating layers to trap enormous amounts of oil and gas. So, sequence stratigraphy gives us the key to read our planet's incredibly dramatic history, a story of rising and falling seas that's written in stone. And that leaves us with one final, pretty crucial thought. We are living through our own period of rapid sea level change right now. So, a few million years from now, what story will the rocks tell about us?